Imagine the entire universe concentrated into a point smaller than an atom. A point so minuscule yet containing all the energy and matter that would eventually form everything we know today. This point, called a singularity, was unimaginably hot and dense. It was a state of infinite density and temperature, a condition that defies our current understanding of physics. Then, about 13.8 billion years ago, it happened. The Big Bang. This monumental event marked the birth of our universe. It wasn't an explosion in the traditional sense, but a rapid expansion. Space itself began to stretch and grow, carrying galaxies and stars with it. The universe burst forth from that tiny point, not into space, but creating space itself as it expanded. This expansion was incredibly fast, occurring in a fraction of a second. Think of a balloon with dots drawn on it. As the balloon inflates, the dots move further apart. As you inflate the balloon, the dots move further apart, just like galaxies in our expanding universe. This analogy helps us visualize how space itself is stretching. The Big Bang Theory is our best explanation for how this universe began. It provides a comprehensive framework for understanding the origins and evolution of everything around us. It's a story written in the language of physics, and it tells a tale of incredible transformation. From a singularity to a vast cosmos filled with stars, planets, and galaxies, the universe was initially a chaotic soup of energy and elementary particles. This primordial state was a hot, dense mixture where particles constantly collided and interacted. Over time, it cooled and expanded, allowing matter to form and evolve. As the universe expanded, temperatures dropped, enabling particles to combine and form atoms. From this cosmic soup, stars, galaxies, planets, and eventually, life itself emerged. The formation of stars and galaxies set the stage for the development of complex structures and ultimately, life. The Big Bang Theory provides the framework for understanding this awe-inspiring journey. It allows us to trace the history of the universe from its fiery beginnings to the rich and diverse cosmos we see today. The very first moments after the Big Bang are shrouded in mystery. This was a time when the universe was incredibly hot and dense, a singularity where the laws of physics as we know them ceased to function. Imagine a point smaller than an atom containing all the energy and matter that would eventually form everything we see around us today. We call this period the Planck epoch, a time so early and extreme that our current understanding of physics breaks down. During this epoch, the four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were unified into a single force. The conditions were so extreme that even the concept of time as we understand it was in its infancy. But as the universe expanded and cooled, things became a bit clearer. The unified forces began to separate, and the universe transitioned from a state of chaos to one where the laws of physics started to take shape. This cooling allowed for the formation of the first subatomic particles, setting the stage for everything that would follow. During the period of inflation, the universe expanded exponentially, like a bubble growing at an incredible rate. This rapid expansion happened in a fraction of a second, stretching the fabric of space-time itself. Imagine blowing up a balloon. In an instant, it goes from a tiny speck to a vast expanse. This inflationary period smoothed out any irregularities, making the universe appear uniform on a large scale. This rapid expansion smoothed out the early universe, explaining why it looks relatively uniform today. The tiny quantum fluctuations that existed before inflation were stretched to cosmic scales, seeding the formation of galaxies and large-scale structures. These fluctuations are the reason why we have galaxies, stars, and planets today. As the universe continued to cool, energy began to condense into matter and antimatter, which annihilated each other upon contact, releasing more energy. This process was incredibly violent, with particles and antiparticles colliding and converting into pure energy. However, this wasn't a perfect balance. But luckily for us, a slight asymmetry favored matter, allowing it to persist and form the building blocks of everything we see. For every billion pairs of matter and antimatter particles, there was one extra matter particle. This tiny imbalance was enough to ensure that matter dominated the universe, leading to the formation of atoms, stars, and galaxies. Then came the era of nucleosynthesis, where protons and neutrons combined to form the first atomic nuclei, primarily hydrogen and helium. This process occurred within the first few minutes of the universe's existence. These light elements are the most abundant in the universe and serve as the building blocks for more complex elements formed later in stars. Over hundreds of thousands of years, the universe cooled enough for electrons to be captured by these nuclei, forming neutral atoms. This process, known as recombination, marked a significant milestone in the universe's evolution. The formation of neutral atoms allowed the universe to become transparent to light, setting the stage for the next era. This period, known as recombination, allowed light to finally travel freely through the universe. Before recombination, the universe was a hot, opaque plasma, where light couldn't travel far without being scattered. With the formation of neutral atoms, photons could travel vast distances, filling the universe with light. This first light, now stretched into microwaves, is what we observe today as the cosmic microwave background radiation, a faint echo of the Big Bang. This radiation provides a snapshot of the universe when it was just 380,000 years old, offering invaluable clues about its early conditions and subsequent evolution. The cosmic microwave background is a relic of the universe's infancy, a time capsule that allows us to peer back into the very origins of everything we know. The cosmic microwave background, CMB radiation, is one of the most compelling pieces of evidence supporting the Big Bang theory. This faint glow of radiation which permeates the entire universe is a relic from the early stages of the cosmos, dating back to approximately 380,000 years after the Big Bang. It provides a snapshot of the universe when it was still in its infancy, offering invaluable insights into its origins and evolution. Imagine looking at the faint afterglow of a massive explosion that happened billions of years ago. This afterglow, known as the CMB, is like a cosmic fingerprint, a remnant of the intense heat and energy that filled the universe shortly after its birth. It is a silent witness to the dramatic events that shaped the cosmos. That's what the CMB is, a faint glow of light coming from every direction in the universe. This radiation is remarkably uniform, but it contains tiny fluctuations in temperature that reveal a wealth of information about the early universe. These fluctuations are the seeds of all the structures we see in the universe today, from galaxies to clusters of galaxies. It carries information about the early universe, revealing its temperature, composition, and structure. By studying the CMB, scientists can learn about the conditions that prevailed in the universe's first moments, including the distribution of matter and energy, the rate of expansion, and the processes that led to the formation of galaxies and other cosmic structures. Another crucial piece of evidence comes from the work of astronomer Edwin Hubble. In the 1920s, Hubble made a groundbreaking discovery that would forever change our understanding of the universe. Using the powerful telescopes of his time, he observed that distant galaxies are moving away from us, and he noticed a pattern in their motion. In the 1920s, he observed that galaxies are moving away from us, and the farther away they are, the faster they seem to be receding. This phenomenon, known as the redshift, occurs because the light from these galaxies is stretched to longer wavelengths as they move away, making them appear redder. Hubble's observations provided the first direct evidence that the universe is expanding. This observation, now known as Hubble's law, suggests that the universe is expanding just as the Big Bang theory predicts. The discovery of the expanding universe was a monumental breakthrough, confirming that the cosmos had a beginning and has been evolving ever since. It also implied that if we trace the expansion backward in time, we would reach a point where the universe was incredibly small, dense, and hot. The abundance of light elements in the universe also supports the Big Bang. According to the theory, the early universe was a hot, dense soup of particles, where nuclear reactions occurred at a rapid pace. These reactions produced the lightest elements, primarily hydrogen and helium, in the first few minutes after the Big Bang. The theory predicts that the early universe was hot and dense enough to produce large amounts of hydrogen and helium, the two lightest elements. These elements were formed through a process known as Big Bang nucleosynthesis, which occurred within the first 3 minutes of the universe's existence. The precise amounts of hydrogen and helium produced during this period are in excellent agreement with the observed abundances of these elements in the universe today. These predictions closely match the observed abundances of these elements in the universe today. The consistency between the theoretical predictions and the actual measurements of hydrogen and helium abundances provides strong support for the Big Bang theory, It shows that our understanding of the early universe's conditions and processes is on solid ground. Finally, the large-scale structure of the universe, with its vast clusters of galaxies and immense cosmic voids, also aligns with the predictions of the Big Bang theory. The distribution of galaxies and the patterns of their clustering are not random. They reflect the initial conditions set by the Big Bang and the subsequent evolution of the universe. By studying these structures, scientists can trace the history of cosmic formation and growth, further validating the Big Bang model. Section 4. The Expanding Universe and Hubble's Law. Hubble's discovery of an expanding universe revolutionized our understanding of cosmology. Imagine dots on a balloon again. As the balloon inflates, every dot moves away from every other dot. Similarly, in our universe, galaxies are not just moving through space, but space itself is expanding, carrying the galaxies along with it. This expansion has profound implications. It means that the universe had a beginning, a point in time when everything was much closer together, and it suggests that the universe will continue to expand, potentially forever, becoming colder and more diffuse over time. Hubble's law allows us to estimate the age of the universe. By measuring the rate of expansion, we can rewind the clock back to a time when everything was compressed into a single point, the Big Bang. The current best estimate for the age of the universe is around 13.8 billion years. Section 5. Cosmic Implications, Space, Time, and Us. The Big Bang Theory has profound implications for our understanding of space, time, and our very existence. It tells us that space and time are not absolute but are interwoven into a fabric called space-time, which itself was created in the Big Bang. The theory also provides a framework for understanding the evolution of the universe from a hot, dense state to the complex structures we observe today. Furthermore, the Big Bang Theory explains the origin of the light elements, the existence of the cosmic microwave background radiation, and the large-scale structure of the universe. It has revolutionized our understanding of the cosmos and our place within it. The Big Bang Theory also raises profound philosophical questions. If the universe had a beginning, what came before it? What is the ultimate fate of the universe? These questions continue to captivate scientists and philosophers alike.